All right, so our vocabulary. Hopefully you've done your warm-up. Our first one, seafloor spreading is C. Our next one, trench, is A. Number 3, our mid-ocean ridge is D. Number 4, continental drift is E. And our last one, plate tectonics, then, is B. This is Unit 2, the ocean floor. We're going to be talking about seafloor spreading and plate tectonics. Target for the day is 2.A, our plate tectonics theory, and we're going to be able to define that theory. So in the early 1900s, we came up with some new technology called sonar. It stands for sound navigating and ranging. This is going to detect objects underwater by transmitting a sound and receiving an echo. Based on the echo's angle, time to return, and frequency change, sonar operators can determine where an object is, its exact distance, and whether or not it's moving. German meteor expedition in 1925 used it to map the South Atlantic Ocean floor. Remember, this is where we started finding our mid-Atlantic ridge and that the ocean floor is not flat. And then our Atlantis expedition in 1931 used it to confirm the existence of the mid-Atlantic ridge and mapped it. And then our Britain's HMS Challenger 2 expedition in 1951 used it to confirm the existence of marine trenches. So number 1 on your notes, what new technology enabled us to learn about the seafloor? That is sonar. So in 1960, our geologists Harry Hess and Robert Dietz proposed our seafloor spreading theory. They said basically that new crust emerges from the Rift Valley in a mid-ocean ridge. Okay, so what's going on is that the magma from the asthenosphere pushes up through a rift or break and then solidifies into new crust. And now as it's solidifying, it's building up on top of itself, so it's creating a ridge. This new seafloor near the ridge then continuously pushes old seafloor away from the ridge so that you have plates moving in opposite directions away from the ridge. Other scientists then proposed that our old seafloor is going to subside or subduct at our trenches. So our cool, dense seafloor is drawn down by gravity and inertia. Plus the convection that's going on underneath helps to pull it along as well. So over here towards the mid-Atlantic ridge, you'd have hot stuff coming up and then pulling this down and cooling and coming back down. So our actual theory states new seafloor forms at our Rift Valley at the center of a mid-ocean ridge, spreads away from the ridge due to convection currents, and returns to the asthenosphere at subduction zones, or our trenches. So when we look at this, this is where our hot stuff is coming up, and then it starts to cool, so it drops down, and gets heated back up by the magma below. So these are our convection currents in our asthenosphere. Some of it is going to escape up to the surface or a mid-ocean ridge, okay? And then our plates are going to move away and subduct at what we call our trenches, okay? So for number 2 on your notes, this side, remember, hot stuff goes up. So we're going to say that's hot. Next side, cool stuff sinks, so that side's cool. In the center here, this is our mid-ocean ridge. So our Canadian geophysicist John Tuzo Wilson combined the two theories in 1965 to form plate tectonics theory. I want you guys to understand that this man really did not do a lot of work. Basically, he took Alfred Wegener's theory of continental drift, which had no process. Remember, Alfred Wegener said that the continents were basically plowing through the ocean floor. He takes that theory and he says, wow, I think seafloor spreading theory could give a good process for why our continents are moving around and why they fit together like puzzles. So he just takes the two theories, combines them together, and ta-da, plate tectonics. So what it's actually saying is that our Earth's lithosphere consists of more than a dozen separate plates that are in constant motion. Some are entirely oceanic, some are entirely continental, and then I would say a majority of them are a combination of both. So number 3, what is plate tectonics theory? It is simply continental drift plus seafloor spreading gives us our plate tectonics. Number 4, last one on our notes, how is plate tectonics theory different from continental drift theory? Remember, Alfred Wegener had a really bad process for continental drift. So plate tectonics is better because now we have a valid process, and that valid process is seafloor spreading. The seafloor spreading enables us to say, this is how the continents are moving around. So it is a valid process. Once you get this written down, you are going to turn in your notes into the box. You're going to grab a ruler, and you're going to grab some colored pencils, the colors that are listed at the bottom of the first page on your activity. All right, so looking at today's activity, we are going to basically calculate the rate of seafloor spreading. I don't want you to freak out because everyone hates math. Okay, this is all very straightforward. You just have to follow the directions and read the steps, and you can do this math. Okay, you can use a calculator, you can use this calculator on your cell phone, however you want to do it. So the first thing we need to do is we need to set up the map on the activity. Okay, I want you to notice up here it gives us our scale. This is 1 centimeter equals 379.2 kilometers. Over here we have Africa, and over here we have North America. So first thing we need to do is set up a line that we're going to measure along. So I want you to go from point A over here to point B, and you're just going to draw a straight line, straight across. So just connecting the points between point A and point B, draw a line straight across. Now we need to highlight our mid-Atlantic ridge with red. Okay, our mid-Atlantic ridge is our 0 line here. It's 0 because it's 0 years old. This is our new or baby rocks. Okay, so they're very young right here at the mid-Atlantic ridge. This is where they're coming up from the asthenosphere. So highlighting it in red, just like that. Now the rest of the lines that we draw, we want to keep pretty much parallel to that, but we're also going to make sure that it's intersecting right at the line that we previously drew. So you're going to highlight your 20 million year line on either side of the mid-Atlantic ridge in gray. Your 35 million year line is in pink. Your 55 million year line is in blue. Your 84 million year line is in yellow. Your 118 million year line is in green. Your 156 million year line is in orange. And your 180 million year line is in purple. Now for those last two, you're going to make sure they go through point A and point B. Okay? Again, notice how all of the lines are pretty much parallel. Give you a moment to make sure that's all set up. Now, we're going to start measuring the distance of these lines. The first one we are going to do together. This is part B on the exercise. Okay, so what we're going to do is we're going to put our ruler down here, make sure 0 goes on 0. In our first one, we are measuring over to our 55 million year line. We're always going to measure over to the right side. So when Miss S does this on a piece of paper, I end up with 1.5 centimeters. Okay, so for number 1 in part B, where it says record your measurement here, put 1.5 centimeters on that line. Then the next step we're going to do, we're going to convert kilometers, knowing that 1 centimeter on the map equals 379.2 kilometers on Earth's surface. This is where we're going to show our work. So we're going to take our 1.5 centimeters that we measured, and we're going to put it on this first line here. Okay. Now we have to convert this into kilometers. This is my conversion. I know 379.2 kilometers is equal to 1 centimeter. When I do the math, my centimeters would cross out or cancel out, so that I'm left with 1.5 times 379.2 kilometers. When I do that math, I come up with 568.8 kilometers. Again, that's 568.8 kilometers. Now on to step 3. We're going to convert our distance into centimeters by multiplying by 100,000. That's because there's 100,000 centimeters in every kilometer. Okay, we're going to do the conversion the same exact way. So on this line, how many kilometers do we have? We have 568.8 kilometers. So we're going to multiply that by 100,000 centimeters is the same as 1 kilometer. So I cancel out my kilometers. I'm left with 568.8 times 100,000 centimeters, and that is going to give me 56,880,000 centimeters. Again, it's 56,880,000 centimeters. Now on to step 4. We're going to figure out the rate of the seafloor spreading. Okay, so we're going to put our centimeters that we calculated right here on the top line, our 56,880,000 centimeters. Now remember, from step 1, we're dealing with our 55 million year line. So our years down here, we're going to put 55 million. Then all we have to do is simple division. So we have our 56,880,000 divided by 55 million. That is going to give us 1.03 centimeters per year. So we know from our 0 to our 55 million year line, it moved 1.03 centimeters a year. Now you're going to have to do 4 more calculations on your own, which is part C. Again, just follow along step by step, filling in the blanks as you go. Then you have part D, which is going to ask you to do a couple of questions, plus you're also going to have to figure the average rate using all of your calculated rates. So you'll take all of your calculated rates, you're going to add them up, then you're going to hit equals, and then you're going to divide by 4. That will give you your average rate. Okay? Any questions? Please ask Mrs. English. She's a brilliant lady, and I'm sure she can help. I will see you guys next class.